All right. All right, so we're on to now the collision theory. So now the collision theory deals with exactly what it sounds like. This idea that we're forming chemical reactions through reactants colliding with each other. I can't get this to move this up. There we go. And remember, they must come in contact. So let me just increase this. So if you don't have this, this is in that packet. We're talking page 17 in the packet. So the basis of a chemical reaction, again, we're studying how fast is it happening? How fast is the chemical reaction occurring? The collision theory tells us that the reaction will only take place when the reactants come in contact. So they come in and they collide. The collision requires a certain minimum energy known as the activation energy. Now, the new one that we're going to talk about today is this idea of collision being in a certain orientation. So they actually have to collide in a certain manner. An easy way to describe this, say we have something that's pentagon shaped and we have something that's square. And let's say the only place that this thing can collide and actually make a reaction occur is when this side right here hits this side right here. So you can see at the orientation and at the angle that they're headed towards now, as they come together, and collide, as long as they hit right there and right there, there will be a chemical reaction. But if this thing is twisted a little, if it hits that side or the tip or this tip over here or anywhere else, that's what orientation means. So in this three-dimensional orientation, you'll see I have some animation to show you coming up with that. So if the reactants do not collide, or if they collide with an energy that is lower than the activation energy, or if they collide with the wrong orientation, they mentioned there, none of those are going to be chemical reactions. So all three of those must be met. You have to hit in the correct orientation with enough energy. Remember to knock their books out of their hand if you want to, going back to that video. Most chemical reactions take place via a series of steps. Those steps are referred to when you're doing that as elementary steps. So the elementary steps give us an overall reaction. It could occur in a single step. It can occur in multiple steps. And we see these, so these are those reactants and products graphs I had you do. Remember, the activation energy is the energy that you had to add to get to what is referred to in this case as the transition state, also known as the activated complex on our graphing assignment the other day. So transition state or activated complex. So that's where they have collided and they have not yet broken the bonds. So this mass of reactants all jammed together. All right, so they can be unimolecular, meaning it happens in one step. For example, a single species is reacting in order to form products. So you see how we only have one reactant? We call that unimolecular. Uni, not mono, uni. And then not di, but bimolecular when you have two. So you can see we need an NO and an O3 to hit right there in order to get that reaction to occur. And then you could have tri or termolecular, where you have to have three molecules occurring. Now think about the odds of this reaction right here occurring in one step. You have an NO molecule. So an NO, you have a second NO molecule, and now you have an O2 molecule over here, and all three of these have to meet those three requirements. They have to collide, so they have to collide at the same time, three molecules. They have to hit with enough energy, but the big one, besides colliding, is they have to hit with the correct orientation. If they do not hit with the correct orientation, for example, if these are the N's and these are the O's, and as these O's come here and collide in this manner, even if they were twisted this way and they collide in that manner, would they get a chemical reaction? Well, that's the question. So now, would that happen in one step? Very unlikely that it would happen in one step. So what we have instead is something called a reaction mechanism. So this reaction is probably going to occur in a series of steps. So let me get rid of what I have here. So Here's another one of those energy diagrams. So one that occurs in more than one step. We saw those as well. So the reactants over here are the products, and then in the middle are those intermediates. So we have the first transition state, or the first activated complex, which required, that amount of energy right there, gave us intermediates. So you can see the first step was exothermic. The second step has an activation energy, and this right here determines which one is going to go faster or slower. Remember, the lower activation energy, the lower the activation energy, the faster. Higher the activation energy, the slower. That's the rate determining step. And then you can see, once again, we have now the overall delta H. And then we also have a delta H of the second reaction. So all of those were exothermic in this case. All right, so I'm referring back to that picture, but we watched this video. I don't want to watch it again, but it's still there. So if you're confused as to how we make a chemical reaction happen, or where is some of this idea of collisions coming from, go back and watch this. As I said, my favorite chemistry video for several reasons, but one is that it's very applicable to what we're doing. Let me switch this to best fit. Let me see if I missed anything on that last slide. I don't think no, that's just the video. Okay, so I was talking about orientation. I was trying to draw a picture, and then when I went to do this, and I created this flip chart, years ago, I always had this animation to show you where the orientation was either correct or incorrect. See, if I clicked incorrect orientation, it would hit as it is right now, because one of the products to this is Ki. So the K has to hit the iodine. And if it hits in this angle right here, even if it has enough energy, it's the wrong orientation. But if we were to flip this molecule around, and then the purple hits the potassium, then you get the reaction that you're looking for with Ki. The problem is it's a flash animation. And if you've been paying attention to anything with computers, flash ended on December 31st of this past year. So I had to find a new one. So here's what I got. There's actually sound. Let me turn the volume on. I don't know that you'll be able to hear it all the way over there with the microphone, but here goes. I'll shut up.
For two molecules to react, they must collide. If an ozone molecule and a nitrogen monoxide molecule meet without enough energy to overcome their bond energies, a reaction does not occur, and the molecules separate without reacting. For two molecules to react, they must collide. If an ozone molecule and a nitrogen monoxide molecule meet without enough energy to overcome their bond energies, a reaction does not occur, and the molecules separate.
All right, so that would be they hit with the correct orientation, but not enough energy, as she said.
If the two molecules collide with sufficient energy to overcome the activation barrier, but with an orientation that does not allow new bonds to form, no reaction takes place. The molecules will separate unreacted.
All right, well then, what about if it does?
If a collision occurs between the two molecules with sufficient energy and the proper orientation, then a reaction can take place to produce molecules of O2 and NO2.
I'm going to play that one more time.
If a collision occurs between the two molecules with sufficient energy and the proper orientation, then a reaction can take place to produce molecules of O2 and NO2.
So that's what we mean by proper orientation. So they literally have to physically collide in the correct order. All right, so we're going to look through a bunch of reaction mechanisms here. So reaction mechanisms are, as I said, the series of steps that lead to the overall reaction. Each individual step is called an elementary step, and the overall elementary steps, when you add them up, will give you the overall reaction. You can have unimolecular, remember, where there's only one. You could have bimolecular. You could also have termolecular. These describe literally what is happening at the atomic scale. So all the way down to the atomic level, which bonds are breaking in which order. The sum of the elementary steps must give you the overall balanced equation. We'll see that in a second. They must also explain the experimentally determined rate law. Remember, rate laws are not given by stoichiometry. You have to do the actual experiment and do our rate determining step in our rate laws. Doubling it, tripling it, quadrupling it, etc. The rate determining step is always the slowest step. We consider the other ones to happen really fast, instantaneously. One of the steps, though, is really slow, and that's what we call the rate determining step. Now, the way you're going to see that in these is they'll literally be labeled fast or slow, as you can see. All right, so let's just jump in and try it. So here's our overall reaction. 2x plus y yields z. Deduce the rate law, and then calculate the value of k with the correct units. All right, so our two reactants are x and y. Remember, you do not include products in a rate law. I'm just going to run through it quickly. Right here, this is doubling. So 2 to what power equals? See, that stayed the same. That didn't change. So it is 0. So it's 0 order. In other words, we're just going to take it right out of the rate law. I'll do that one. So that's doubling. So 2 to what power equals? Also doubling. So it's first order with respect to y. So it's 0 order with respect to x, first order with respect to y. Rate equals k times y to the first. Plug them in. 7 times 10 to the minus 4. K times 0.1 to the first. 7.0 times 10. So we're dividing by 0.1. 10 to the minus 1. Subtract them, negative 4. So negative 3. And the units, 1 over seconds. Remember, it's always 1 less than the overall order. If you add the overall order here, it's first order overall, which means the molarities cancel and you get 1 over seconds. All right, good there. The following 3 mechanisms have been proposed. The species M and N are called intermediates. Intermediates in that they're formed in earlier steps and then consumed in later steps. What is the overall reaction of each? What is the molecularity of each step? And then what is the rate law derived from each? And which mechanism is consistent with the rate law in part A? So the part A rate law, what we're looking for is rate is equal to k times y to the first. So let's do the overall reaction first. Now, I don't want to cross them out yet because I don't want to confuse you, but you can see that an M, I will cross it out, but I'm going to erase this. So an M and an M cancel. Why? Well, because one's on the product side and one's on the reactant side. So then the sum total is 2x plus y yields z. And that was our overall reaction. 2x plus y yields z. So this is a valid mechanism. So that's the first step, the thing you got to check. Is it a valid mechanism in that it gives us the overall reaction? The intermediates cancel when they're supposed to, and it does. So now what we do for the rate law is the slow step determines the rate law. And here's how easy these are. It's the stoichiometry of the slow step, meaning you take the reactants, x, and you raise it to its exponent, 1 and then y to the first. Now this is the rate law that we want according to our part 1 up there where we found the rate law. This is the rate law we got with this mechanism. So this is not a correct mechanism. Yes, it is an overall reaction, but the slow step does not give us the correct rate law. So that's how it works. You do the stoichiometry of the slow step. So if I start with that this time, rate is equal to k times y to the first. The slow step, y to the first. So that is the correct rate law, y to the first. Let's do the overall reaction. So we have an M being produced and then an M being used up. And so we have x plus y yields z. So this one is also wrong. What's wrong this time is the overall reaction does not give us the 2x that it's supposed to according to the balanced equation. All right, so this time, once again, we can do the rate law right away. It's always the slow step and it's the stoichiometry. So the rate law is correct again. What about the overall reaction? So we have an M being produced in the first step, used up. We have an N being produced and used up. If I do the sum total, you can see I do get. So this one has the correct overall reaction and it has the correct rate law. So mechanism 3 would be the right answer to this. Mechanism 3 is going to give us the correct overall reaction and the correct rate law. All right, so we got to add to this. Before we add to it, we need to discuss something called the law of mass action. And that's what this is. We're going to learn equilibrium next. Equilibrium is where we start going in both directions. We've always gone reactants to products. In equilibrium, the products start becoming reactants. And now you have this flow going in both directions. When you do this, you write something called an equilibrium constant, K, capital K. We did capital K when we did ln of K with delta G, if you remember that equation. So this is the K we're talking about. Here's what we need to know. We need to add to this. K is equal to the products over the reactants in terms of concentration. You multiply them. You don't add them. You multiply them. And here's the big one, is that the, I don't know if I have it written. I don't have it very clear there. So I'll just write it. So the coefficients of the balanced equation become exponents. So the coefficients of the balanced equation become exponents. So we have this new constant, capital C. And what it is related to is we have the rate of the forward reaction. That's what the KF stands for. And the rate of the reverse reaction, or the backwards reaction, going that way. If you rearrange them, you get a ratio of the two rates. And you can see that if this is the overall reactions, the products, the coefficients from the balanced equation become exponents. And then the reactants are on the bottom. And then once again, the coefficients become the exponents. All right, why am I showing you that? Well, because we haven't learned equilibrium yet, but you need to get it in order to get this next step, because you're going to find now these fast equilibrium steps. All right, so often there are equilibrium steps. We usually assume that they're not the rate determining step, although you'll see that it usually specified. We have to do this law of mass action, which I just explained. So let's try it. Well, we can come right in and do the rate law. N2O2 times H2, both to the first power, right? The coefficients in front. All right, now here's the problem. The problem is we have an intermediate in the rate law. And you cannot have intermediates in the rate law. How do we deal with it? All right, first, determine the overall reaction. All right, I can see I have a N2O2 being produced and then used up. I have an N2O produced and being used up. And it looks like we're good now. So we have 2NO plus 2H2 yields N2 and 2 H2Os. Notice that gives us a balanced reaction. 2 N's, 4 H's, 2 O's on both sides. We're good. Are there any intermediates? Yeah, there sure are. We have N2O2 in the first one being used up in the second one, and then we have N2O being produced in the second one and used up in the third one. Determine the rate law. Intermediates may not appear in a rate law. Now, the reason for this is, remember, when we're doing rate laws, we actually use the initial concentration, because the initial concentration we can set very well. We can set it very well because we determine the setup of the experiment. So if I want to start with 1 molar, I could. Then maybe I want to keep B at 1 molar and change this one to 0.5. We can do that. So, or change it to 3. We can do that. With intermediates, they're being produced and then used up. So not only are they difficult to manage the concentration, they're very hard to even find the concentration, because once again, they're being produced and then they're being used up. All right, so we don't include them in rate laws. So what do? So we use the equilibrium expression, that law of mass action, and write the rate law only in terms of reactants. So here's our overall reaction. Remember what we said, only reactants exist in the rate law. So here's the rate law that we wrote according to the slow step, and there's that intermediate. So what I have to do is substitute in, go back up here, how is the intermediate produced, and then relate that to the reactants that produce it. So you can only express the rate law with what it is you're starting with in the beginning. Reactants, not necessarily in step 1 though, you can see this one's in step 2, but you can't not have a reactant from the overall reaction. All right, so N2O2 can't be there. So what I'm going to do is I'm going to write the K expression, and I'm going to put the products, N2O2, over the reactants, NO. Remember, coefficients become exponents. And now I'm going to set them equal to each other. In other words, what is this equal to? So I'm going to multiply both sides by NO squared and divide both sides by K. And now really I have this K on this side, I have a K here, and I have a K here. Those Ks cancel, and that's where we get that capital K. So you're essentially setting the products equal to the reactants from now on. So there's the product, N2O2, coefficient of 1. There's the reactant, and there's what they're equal to. So now I know what that's equal to, so I can substitute it in and then express my rate law in terms of reactants only. So N2O2 is equal to NO squared. Again, going back to, and now we have the correct rate law. So what is the overall order of the reaction, I should say? So it's second order with respect to NO, first order, third order overall. What is the molecularity of the rate determining step? Rate determining step was step 2, and I have 2 molecules. So it is bimolecular. All right, so the next one we need to learn then is, what about a catalyst? So catalysts, we know, speed up a chemical reaction. You probably have learned that. They speed up a chemical reaction, but they don't actually take place in the reaction. Now, that's the way it's usually worded. What that means for us is you're adding it in the beginning as a reactant, and it ends up as a product in the end. So that does cancel out in the overall reaction, but it is something we're adding so we can know the concentration. So catalysts can be included in a rate law. Intermediates cannot, catalysts can. So another component of the mechanism is a catalyst. These are components that change the reaction mechanism and provide a pathway with a lower activation energy, correspondingly a faster reaction. They are a reactant in an early step and a product in a later step, so they do not appear in the overall reaction, but they do appear in the rate law. Again, because we can change the concentration and know the concentration. All right, so let's write the overall reaction again. So we're doing the sum total. I'm just going to underline the ones that cancel. So you can see I have an Mn plus 3 and an Mn plus 3. So I'm going to go right down here and answer this. That's an intermediate. I have Mn plus 4 being produced and then Mn plus 4 being used up. That's also an intermediate. I have 2C E plus 4. So my overall reaction, it looks like, is going to be 2Ce plus 4. Now notice I have an MnO2 in the beginning and I have an MnO2 at the end. So that's going to cancel, but MnO2 is not an intermediate. It's not being produced by one step and then used up in another. We're adding it as a reactant. We're adding it as a reactant. And so that's the difference between an intermediate and a catalyst. So this is the catalyst, Mn plus 2. Our other reactant then is TL thallium plus 1. Now we would normally write our catalyst right there above the arrow if we wanted to, or we could just write it off to the side and say it's a catalyst. So you can see I have 2Ce plus 3s and I have a TL plus 3. So TL plus 1 is a reactant. This is a product. Ce plus 4 is a reactant. And Ce plus 3 is a product. Assuming that the catalyst is involved in the rate determining step, what is the rate law? So we're saying that this is the slow step. So rate equals K times Ce plus 4 to the first and Mn plus 2 to the first. So first and first order with respect to each. Why is an uncatalyzed reaction so slow? Well, look at the reaction. It is molecular. You have to have 3 molecules hitting with the correct orientation with enough energy to make the reaction happen in one step, but it doesn't. It happens in a series of steps. All right, under certain conditions, the reaction NO. So hit pause for a second, try this one. And then if you want to, you can start watching the answers or keep going right to the next page and try that one as well. And then keep going on to the next page and try these 2 questions on the next page. All right, I think you have that. I'm not actually positive you have that in your packet now that I think about it, but I'll make sure it's there. So keep going. All right, answer to number 4. Under certain conditions, the reaction 2NO plus Cl2 is found to be second order in NO and first with Cl. So rate is equal to K times second order with NO and first order with Cl. Given the following mechanism, what are the relative rates of the two steps? Well, if this one is the slow step, the rate is equal to K times NO times Cl2, which is not right. So automatically I know that this one must be the slow step. Why? Well, because the first one doesn't give us the correct rate law. Now, how is the second one? Well, there's that equilibrium. And if we did the second one, I'm going to do it down here so I have a little more room. I would get NoCl2 and I would get NO. Now, NoCl2 is an intermediate. It's produced in one step and used up in another. So we can't include NO. But by looking at the reaction up here, I see that NoCl2 is equal to, remember, it's equal to what's on the other side of the double arrow. Coefficients become exponents. They're all ones. So first, and first. So now I know NoCl is equal to NO times Cl. If I take that now and plug it in over here, I get rate equals K times NO times Cl2. So plugging those two in times NO, which gives us NO squared Cl2, which is the correct rate law. It's a little tricky there. Tried to fool you. Hopefully it didn't. All right, next one. It is found that the rate doubled when NO doubled. So if you doubled NO, the rate doubled. It also found that the rate increased by a factor of 4 when the concentration of NO2 was doubled. So which of the following mechanisms is okay with this particular rate? So we now know that the rate law is equal to, so rate equals K times the NO, or 8, I'm gonna do NO first, so that would be squared, because that's this one, and then times H2 to the first. Which of the following mechanisms is or are consistent? Well, first thing we should check is, does the overall reaction okay? So I have an intermediate, and you can see I have two NOs, one H2. So the overall reaction is good. Rate equals K times NO times H2 would be the rate law. So nope, because that doesn't have NO squared. What about the next one? So rate equals K times N2O2 times H2. Well, that doesn't work because N2O2 is a intermediate, but N2O2 is equal to NO times NO, which is NO squared. So if I plug that in, well, that one's good. What about the overall reaction? 2 NOs and H2 and N2. Yeah, so that one has a good overall reaction and it has a good rate law. So yeah, that one's pretty good. Rate equals K times H times NO squared. All right. Again, an intermediate. What is H equal to? Well, H squared equals H2. I need to know what H is equal to, though. So I got to take the square root of both sides. So I end up with the rate is equal to, do you know that so we're equal to, that would be H now, and it would be the square root of H2, which is the same as H2 to the half power times NO. So that one's no good. It doesn't give us the right rate overall. I didn't check the overall rate. It looks like that cancels. So we had to multiply this one. Oh, then we got an H and H and an H. So 2 NOs and H2 and H2O. Yeah, so the overall reaction was good. It's just that our rate was wrong. And the last one, rate equals K NO squared. Well, that one's no good right off the bat because we don't have an H2 in our rate law. That cancels, that, yes. So our overall reaction, though, is correct. All right. All right, last thing. So this is an old AP chemistry question. So it is proposed that the reaction represented above proceeds via the record below. So you can see right away we can write the rate law now. Let me switch. Actually, I'm good there. Step 1 of the proposed mechanism involves a collision between an NO and an F. This step is slow enough such that the collisions occur very frequently. Consider a specific collision between an NO and an F. One factor that affects whether a collision will result in a reaction is the magnitude of the energy. Explain. You have to overcome activation energy. So you have to hit with enough energy to overcome the activation energy. Identify and explain one other factor. Orientation. Remember, it has to hit with the correct energy and the correct orientation. Considering the following potential rate laws for the reaction, circle the rate law that is consistent with the reaction mechanism above. Well, we always choose the slow step. So rate equals K times NO2 times F2. So each to the first power. Notice the stoichiometry does not matter. So the correct answer is that one. And it says, explain your reasoning behind your choice. Well, the slow step is what determines the rate law and the stoichiometry of the slow step. Diagram above, the potential energy. So these are very popular. There's A plus B yields C. So there's our overall reaction. You could, so on the diagram above, which represents the delta H for the reaction? Well, delta H is the energy from the reactants to the products. And so right there is the delta H. This one would be the activation energy. This would be the energy from the activated complex or the transition state all the way down to the products. All right, so if you have any questions, let me know.